Okay, 8.2, derivatives of exponential functions. The origin of e. So if you haven't heard of e yet, e is an irrational number, just like pi. It's non-repeating, non-terminating decimal. And Leonard Euler, this guy right here, made many contributions to math. However, one of the most recognized contributions in his development is this irrational number denoted by the letter E. Probably it's called Euler's number because he designed it, so the E is probably just from his last name. And it comes from this, it's developed from this compound interest situation that he figured out. So just look at this for a second. You don't have to ever reproduce this, of course. Recall the formula for calculating compound interest, okay? So we actually made this a little bit different. We said that A was equal to P1 plus R on N to the exponent Tn. We just adapted it a little bit. But the I represents the interest earned. And in this scenario, we're going to do 100% interest each year. Yeah, right. Not likely, but just to show what's going on here. So if you invest $1 for 1 year, at the end of the year, our invested capital has grown to 1 plus 1 on 1. Okay, so where are all these ones coming from? Okay, so this is the formula one. That's the formula one. This is for 1 year, okay, compounded for the 1 year. So that would be the one as well up there. And then this last one is representing the 100%. So if you make 100% on your $1, you should have $2 when you're done. So then we go back to the bank and we convince them that after 6 months, they should give me my interest. And then that gets added to the capital, and then we get interest on top of that capital, which is how compound interest works, which is why we now have this 2 in the bottom, because now we are compounding, we are calculating it twice in 1 year, which is also where that 2 is coming from. And so we make more money. And so the pattern continues. So now what happens if we did it for 3 times in a year, 4 times in a year, etc., all the way down? So you can see as we go down, as we increase the number of times we're calculating the interest and adding it into our total money, that we are gaining more money. However, it starts to look like it's approaching something. So as n gets infinitely large, what happens to the final amount here is it actually approaches this funky irrational number e. And here it is, correct to 30 significant numbers. So how we always say that pi is approximately 3.14. E is approximately 2.71, okay? And it's defined as Euler's number. So that's the background behind it. You don't have to be able to figure out why he did it, how he did it, anything. That's just the background to this E. Now, what happens if we took a graphical approach to this function, and I just put x's where there was n's, and we used a standard window setting, almost, where I cut and paste. You can see, obviously we have a pod here because we have this 1 on x element in our equation, so we have a non-permissible number. But both on the left side and on the right side, we have that the graph is approaching this horizontal asymptote. And so as we get infinitely large, both on the negative side and on the positive side, the graph is approaching, funky enough, it's approaching E. So E was discovered by Euler. We don't have to know how, why, whatever. He did the tough work for us. We just have to understand that it exists and that there's this limit. As x approaches positive infinity of this function, we're going to E. As we approach negative infinity of the function, we're also going to E. Okay, so that limit exists. It's called the fundamental limit of exponential function. We have a few of those, don't we? All right, so What about the graph? So if we have the function f of x is equal to e to the x, well, that's, we looked at 2 to the x and 10 to the x, etc. in the previous lesson. Well, e is just approximately 2.71 being raised to an exponent. So it should look like an increasing exponential graph, which it does. The really cool thing about this graph is that e to the x is its own derivative. This is just cool and weird and everything in between. So what does that actually mean? So it means, when you think back to a derivative, the derivative represents the slope of the tangent line to the curve, to the original curve. So if I think about this point here at x and e to the x, right? If I have the function y is equal to e to the x, and I put x in here, what do I get? Well, I still have e to the x. That's my derivative. So the slope is my derivative. So even at the point 0, 1, why does that work? So e to the x, we're putting in the x value to our function, right? Putting that in here, e to the 0. Oh, well, that's 1. And so the slope is 1. Very, very cool. Okay. Remember that slope equals rate of change. So there's another way to look at this. Let's say we consider a point on the function in which the y-coordinate is 8. So somewhere, who knows where, somewhere along here on this graph, we have a y-coordinate that's 8. Well, then the slope is also 8, the way this graph works. Okay, the instantaneous rate of change at that point would be 8. All right, so that's a little bit of background. It's funky. Euler did all the hard work for us. We just have to know what E is and be able to use it. And his derivative is super easy. It's itself. So what happens if the exponent itself is not just x, right? So what happens if it's e to the 2x, e to the 7x plus 5, something like that? Then we have our chain rule. So we take e to whatever that exponent is, e to the same exponent, and then we follow up with taking the derivative of that exponent of the argument. Okay, so just chain rule, d outer, d inner. So don't forget your dinner when the exponent is something more than x. All right, let's do some. Okay, so we have the function x squared times e to the x. So we have to recognize this is the product rule, okay? So f prime of x is going to be 1d2 plus 2d1. Product rule is so much fun. Okay, so 1 is x squared, right? 1d2. So the derivative of e to the x is just e to the x plus 2, which is just e to the x, d1. And the derivative of x squared is 2x. So once you've taken your derivative, then we want to be able to factor, because we are going to do a little bit of a curve sketch later on, and in factored form is easier to look for critical numbers. So might as well get in the habit right from the get-go. So there's an e to the x in common, and there's an x. So we pull those out, and we would be left with x plus 2. There we go. Next one. What happens if we have e to the power of something ugly times tan 5x? So we have another product rule. Each of those pieces have some arguments that require a chain. So we have a product and a chain. Okay, so y prime is equal to 1. So e to the power of negative 6x plus 2 times d2. So what is the derivative of tan? Secant squared of the argument multiplied by the derivative of the inside. So don't forget your derivative of your argument on the trig as well. So plus, so we have 1, let's just write it up here, 1 d2 plus 2 d1 few little Christmas colors, why not? Okay, so the second function was tan 5x. And the derivative of the first one will be e to the same exponent multiplied by the derivative of that exponent. That's the chain, which would be -6. And then we're looking to see if there's anything that we can factor out. And we have these e's, very, very common that they come out. So we pull that guy out. And then what are we left with? We have 5 secant squared 5x minus 6 tan 5x. There, done. All right. Determine the coordinates of the maximum point. Okay, so here we get in some curve sketching. Okay, so the first thing I need to do is notice that they've given me a restricted domain. I'm looking at y equals e to the power of sine x. So we're putting some trig in with our exponential function here. And I will take the derivative of that. So y prime is e to the same exponent multiplied by the derivative of the exponent is cos, d outer, d inner. And just remember that we are then going to set that equal to 0. That would be the second thing we need to do, and look for critical numbers. Okay, so we're already in factored form. Okay, so the first thing here is e to the sine x is equal to 0, and the second factor would be cos x is equal to 0. Now, remember, we're looking at from 0 to pi. Anytime we're looking at trig, we want to be looking at something that's restricted. Okay, so think about this. E to any exponent, will it ever equal 0? The answer is never. Okay, this is never going to work. And perhaps if you just need to on a piece of scrap paper, think about that. E to the power of 5. Remember, e is approximately 2.71. So that to the power of 5, positive number. E to the 1 is e. What about e to the 0? What is e to the 0? Oh, well, that's 1. So that's a positive number. What about e to the -1? Well, that would be 1 over e to the positive 1. So that'd be like 1 over 2.71. So all of that comes out to be positive, and I just will erase that because you don't really need that. That's just background to why that's not going to exist. And then cos x is equal to 0. Well, when is cos x equal to 0 on my unit circle? It is equal to it at pi on 2 and 3 pi on 2, but I will notice my restricted domain will say no to that 3 pi on 2, and all we care about is the pi on 2. And then we are going to move forward with testing that critical number between 0 and pi and pick a couple of test points. I picked pi on 4 and 3 pi on 4. And remember that those test points will tell you something about the derivative, right? It will tell you something about the function. So when I put pi on 4, e to the power of sine pi on 4, that's going to be a positive number. Times cos pi on 4, sorry. To do both parts. That'll be a positive number because both of those pieces are positive. But when I put in the 3 pi on 4, this will be positive, but cos will be negative. So that's now negative. So I go positive, negative. So I'm going to go from an increase to a decrease. And so I have max happening right there. And that max is happening back in the original function, e to the power of sine pi on 2. Sine pi on 2 is 1. And so we have our max at pi on 2 and e. Perfect! Just in time for the video to end, and we'll come back and try this one. You could give this a go and start it before you start the video number 2 and see how